Hi guys. Give it a minute for other people to join our meeting. How you guys doing today? How you guys doing?
Doing good.
Oh.
Doing good.
Okay, thank you. So I have a quick question for you guys. Most days I post, every day I post lecture videos, right, under our week, right, this is week 1, week 2, week whatever. And then also what I do is if I have questions about like homework problems that we don't go over in class, then I will post detailed solutions to our Canvas page, but I post them to the week in which the homework was originally posted. So like when you guys ask questions about homework for chapter 1.2 and 1.1, I post it to week 1 because that's where the homework is. And would it be helpful if after I post those, I send out an announcement saying, you know, I've just posted stuff to our Canvas page, please check it out? Or do you guys just want to be taking a look yourself every day, or how do you want to do that? I tend not to want to flood you with all sorts of announcements, but if you think you're not going to look unless I tell you, like in an announcement, would an announcement be helpful? You can reply in the chat if you don't want to say it to the class, say it verbally. So announcements, yes or no? He's quiet. Nobody wants to tell me. Sure. Okay. All right. I'll send out announcements. Let's do this. I'll send out announcements when I post new things to our classwork page, and then our Canvas page. If it gets to be too many announcements, like your other classes are also sending, or you have a lot of announcements or whatever, tell me, and then we'll pull back on the announcements, okay? Because I don't want to flood you with so many things, but I want to make sure that you're finding out that there's stuff being posted. Okay, great. So let's see, any questions, quick questions we can spend about 5, maybe no more than 10 minutes on homework questions. I don't want to spend too much time on the homework because we'll run out of time to talk about things in the class. But any quick questions on the homework before we continue on with chapter 1.3? Homework 46 on 1.3. So I'd be happy to talk about the larger numbers, like the higher up numbers on 1.3. But I'll give you the answer. So the answer for 46 is -1/2. You guys don't necessarily have to worry about the higher numbers up on 1.3 right now. I'm going to be looking at, for the quiz tomorrow, looking at more of like the earlier problems on 1.3. And then we can go over the higher problems, you know, later, maybe, you know, on Monday, because we'll also have questions on a quiz next week from chapter 1.3 as well. But I'll pull problems that are like higher in number. So question 46, I hesitate to go over it in detail because we haven't necessarily covered that stuff yet. But the answer for that is -1/2. You want to just know what the answer is so that you can do it. And then we can go over that in more detail next week. But let's see. So what is it? 1.1 question 46 part 8. I think, let me just pull out my 1.1. How far? Okay, so 46, I believe, is one of the questions that I posted a detailed solution to on our classwork page for chapter 1.1. Question 46, I did all of the parts out, A through F, and then you can take a look at that online and then see if that answers your question, because I actually did post that on Monday. That's up on week 1. And it's listed underneath where the homework gets posted that says like chapter 1.1 question 46 detailed solution. You should be able to find it there. 12 on 1.3. Okay, let me see. Let me find mine. Yeah, so we oh yeah, it's just kind of like a it's kind of a funny one. It's a all right, let's see. Yeah, this is kind of like I think a logic problem. Let's see. So so 12 on chapter 1.3. This is kind of a funny one where you kind of have to work your way through it. It's a little bit not quite, you know, worded very well. So you've got the limit as y approaches 7, f of y equals 5. Give me just a sec. Okay, so now I think we were given certain things like f of 7 equals 5 and g of 5 is undefined, right? And then f is continuous, which we actually haven't discussed yet. And then we would say the limit as x goes to 5 of g of x is equal to 7. So some of the stuff we haven't actually had yet in chapter 1.3, we're going to cover it a little bit, but I'll work through this so you can kind of see. So we've got this theorem 1.3.25, which I think they told us to use, which is our limit substitution. Right, so I can say that the limit as x goes to b of g of x equals m, and then the limit as x goes to b of f of g of x is equal to the limit of f of y as y goes to m, right? And so since now b is equal to 5 and m is equal to 7, so I'm doing this here, right? This is the process that I'm using for that one. So then what I'm going to say is that the limit as x goes to 5 of f of g, f of g of x, that's going to equal to the limit as x goes to 5 of f of 7 is equal to 5. Because of that whole limit substitution thing. Okay, this is question 12, chapter 1.3. And part of it, we're using some stuff that we haven't actually quite covered yet. But this is one of the theorems that's listed in our book. Okay. Give you guys a minute to finish writing that down before we go back to chapter 1.3. You guys good with that? All right. Okay, if you guys want to talk about other homework problems, we can talk in office hours too. We can go over in quite a bit of detail in office hours if you want. Talk about those things. All right, so I think yesterday, Monday, when we last met, we were talking about how we evaluate limits, making some kind of a table. Like we covered, we did this problem, we did example 3. We looked at values as, you know, so we're approaching our limit says, let's look at values as x goes towards 0. So I looked at values of x as it approached from the left-hand side, so just a little bit less than 0. I looked at values of x as it approached from the right-hand side, so just a little bit greater. And I looked at my function. What was my function value giving me, right? And so on this particular one, we said that our limit doesn't exist because these numbers, as I approach where my limit, where I'm looking, my numbers are oscillating. I can kind of see this right here as well. My numbers are oscillating in values, right? And so because we're not converging to a specific number, we keep flipping back and forth over and over again. That's a clue that our limit doesn't exist because we're not approaching the same number. It's oscillating back and forth. So on example 4, our limit doesn't exist. Okay, so we're also going to start talking about one-sided limits. So let's talk about, right, so yesterday, excuse me. Okay, so yesterday we were talking about steps to evaluate limits. And then today, right now, we're going to start talking about one-sided limits. Okay, we were kind of doing this already when we built up those tables. I'm going to approach from the left, I'm going to approach from the right. Those are one-sided limits. Okay, so let's write it out. So I'm going to say the limit as x approaches c, some value, negative. It means I'm approaching it from the left. And I'm evaluating that in some function. This is our left-handed limit. Right, I'm approaching at values that are just slightly less than my value of c. The limit as x approaches c from the right, that's our plus of x. This is called a right-handed limit. Okay. This is a really important concept because this is one of our reasons. I'm going to put a bunch of stars here, a bunch of stars here. So our left and our right hand limits must be equal to each other in order for the overall limit to exist. Let's write that down. The limit itself, which is the limit as x approaches c, see there's no left or right of our function, exists if both left and right-handed limits are equal. Right, so in math, I would write it like this. My limit as x approaches c from the left of my function must be equal to the limit as x approaches c from the right of my function in order for this function, in order for the limit as x approaches c to exist. Okay, the left and the right handed limits must be equal to each other. I'll keep putting more stars on that. It's one of our criteria. One of the things we're going to be checking. Okay, I'll give you guys a chance to finish writing that, and then we're going to look at example 5. Okay. So my example 5, we're going to take a look at a left and right hand limits here. Oops, sorry, there's no example 4. Example 5, we're going to take a look at this, our f of x. So a limit as x approaches 0 of x over absolute value of x. Does the limit exist? So I'm going to draw this out just because I like to look at it. Now remember, you're not graded on your drawing or your graphs, okay, unless we tell you specifically like you're going to be graded on this, but typically you're not. So the graphs are just to help you visualize stuff. So we know this function is undefined at x equals 0, right? If I plug in absolute value of 0 is equal to 0, which means I'm going to get a divide by 0 error here. So that means that what I'm looking at is it's undefined, right, at x is equal to 0. So I'm looking at a function that looks like this. Okay. So when I have x over absolute value, I've got positive 1 when I'm dealing with x values that are positive. I've got negative 1 when x values are negative, but it's undefined at x equals 0. So let's write that down specifically. We're going to evaluate left and right hand limits. So I'm going to look at values of x that are less than 0. Not less than or equal to, but just less than. Okay, so what this means is I've got my function of x is x over absolute value of x. So now, if I were to plug in values that are less than 0 for x, that means I'm dealing with a negative x values. I'm taking the absolute value of negative x, right? I'm plugging in values of negative x, which means I'm really dealing with negative x over absolute value of x, which is equal to negative 1. Okay, so if I write this in terms of a left-hand limit, it's going to look like this. The limit as x approaches 0 from the left-hand side, right? Values of x, let's write it out like in red. So I'm approaching these values here. So this is as I approach 0 from the left-hand side. The limit as x approaches 0 from the left-hand side of our function, x over absolute value of x, is going to equal to minus 1. Okay. Now let's do the same thing, but we're going to look at values of x that are greater than 0. Okay. So that means I'm looking at things like this. So my function of x over absolute value of x, which means that I'm looking at positive values of x. whatever they are, +5, +7, positive, which means I'm looking at positive x over absolute value of x, which means I'm going to get a +1 as an answer. I'm going to look at a right-handed limit. I'm going to do limit as x approaches 0 from the right-hand side, x over absolute value of x. I'm going to get a +1. Okay. So now let's take a look, right? I've got a left-handed limit, and I have a right-handed limit. I've got, on my left-handed limit is -1. My right-handed limit is +1. The left and the right-handed limits are not equal to each other, which means, right, I can say the limit as x approaches 0 from the left of my function is not equal to the limit as x approaches 0 from the right of my function, right? Which means I can conclude that the overall limit as x approaches 0, notice how there's no superscript, no like left or right, of my function does not exist. I'm approaching 0 and I'm getting these two different values. One's +1, one's -1. They're not the same as I approach the same value, okay? Which means that my overall limit doesn't exist, okay? Okay, anybody have any questions on this before I move on? That's one of our criteria for limits not existing. Okay. I'm going to move that. Okay, so another criteria for our limit not existing, and we're going to summarize this in just a minute, is if we have infinite limits. Like I go to take the limit as x approaches some value and it's equal to infinity or negative infinity. Okay, so some functions f of x tend towards positive infinity or negative infinity as x approaches some value c. Okay. If this is true, then we say that the limit as x approaches c of that function does not exist because it's unbounded. We'll draw some pictures. We'll do some examples so you can see what that looks like. But it's basically like it's an infinite limit. My function's going to positive infinity, my function's going to negative infinity, right? Infinity is just a concept, right? It's not a number that I can actually use as an example. So it means that our limit doesn't exist because it's unbounded. Okay, so we would say if the limit as x goes to c of my function f of x is equal to positive infinity, or if the limit as x goes to c of my function is equal to negative infinity, that means our limit does not exist. This usually happens around a vertical asymptote. We'll see that. We'll do some examples so you can see what that looks like. Remember, our vertical asymptotes define places where we have typically divide by 0 errors so that we have a domain restriction on our function. Anybody have questions on this before I pull out some examples? Okay, great. So I'm looking at example 6. We've got a bunch of things. I'm going to graph it out just so we can see. Okay, so now this function here, rational function, so I've got 1, x equals 2. I've got a discontinuity at x equals 2. And my function looks like this. Okay. So now if I say my limit, x approaches 2 of my function 1 over x minus 2, right? As x approaches 2, okay, as I'm approaching this value here, as x is approaching 2 from the left and right, my function is going up on one side to positive infinity. my function is going to negative infinity on the left-hand side, right? And my left-hand limit. So this thing here is equal to unbounded. So therefore, it does not exist. Okay. I want to call your attention, though, to this. It depends on where my limit is. If I were to be approaching 3, for example, my function is totally defined at 3. There's no discontinuity there. So my limit as I approach from the left-hand right, so if I say the limit as x approaches 3 of 1 over x minus 2, okay, this does exist. It's going to equal to some number, right? I can plug it in. 3 minus 2, it's just going to be equal to 1, right? From both the left and the right-hand side. It totally exists. So whether or not a limit exists is going to depend on how we're defining that limit. If I approach this area of discontinuity, which is why we use limits, because it's interesting, right? I want to be able to evaluate something that's not defined. I need to be able to use my limit in order to help me do that, okay? But here, right, I can just do a simple substitution. It'll be fine. It'll exist, okay? This one exists. So you always have to be very careful. You have to read what your limit says and what your function says, because sometimes it won't exist, sometimes it will. Okay, let's talk about this one here. So 1 over x squared. So this function, we've got a vertical asymptote. I'm going to draw it just slightly off the axis here, just so you can see that there's an asymptote here at x equals 0. It's undefined at x equals 0. So my function goes like this. Okay, so if I say the limit as x approaches 0, 1 over x squared, right? My function itself is unbounded on either side, right? So as I approach 0, my function goes off to positive infinity. This does not exist because it's unbounded. Okay. On an exam or on a quiz, you just have to say the limit as x goes to 0 of 1 over x squared does not exist. You don't have to tell me like it's unbounded. We're going to use the limit. It's a tool that helps us process things, okay? But just so that you know why it doesn't exist. It doesn't exist because it's unbounded as x approaches 0. Okay, natural log. So again, I'm going to draw this just slightly off my x equals 0. X equals 0. I've got a discontinuity at x equals 0. My function, my natural log function goes like this. As x is approaching 0, my function's heading down towards negative infinity, right? So if I go to take the limit as x approaches 0, now there's a couple of things. The natural log function is not defined for values of x that are less than 0. So I'm just going to say I'm approaching this from the right-hand side. My natural log of x. This does not exist. This is going to be equal to the same thing as the limit as x goes to 0, my natural log of x. But I'm just calling your attention to it. It's not, the function is not defined. So some people, if you want to be super exact about it, you can say I'm just approaching it from the right-hand side. Technically, this is fine too. That also does not exist. Okay. Everybody have those there? All right, so let's summarize our reasons why a limit is not going to exist. So 3 reasons, just to summarize, 3 reasons why our limit isn't going to exist. Okay, as we saw with that sine example, right? As I'm approaching a specific value, my answers, my value for that function are going to oscillate. This is all as x approaches some c value. Okay, we're getting oscillating values. I mean, it's positive, negative, positive, negative, positive, negative. You see this a lot on trig functions. The next reason is that my left-hand limit is not equal to my right-hand limit. Right, we saw that with our absolute value. My function, as I approach the same value, my left and my right-hand limits were not equal to each other. I had different values. So my left limit and my right limit didn't equal to each other. Therefore, my overall limit doesn't exist. Okay, my function's unbounded, right? So my limit, as x approaches some value, my limit's equal to positive infinity, or my limit's equal to negative infinity. That means that my limit is unbounded, which means that my limit does not exist. Okay, so 3 reasons why a limit won't exist. Oscillating values, left and right limits don't agree with each other, they're different, or it's an unbounded limit. Okay. You guys have these? So because the earning isn't the limit infinity. So somebody asked in the chat on 6b, the limit from the left is equal to infinity, the limit from the right is equal to infinity. So because they're equal, isn't the limit also infinity? That's true. Okay, so this is a good question. So here we have 2 reasons on 6a. It's positive infinity, negative infinity. The left and the right are different values, right? One is positive infinity, one's negative infinity. So the left and the right hand limits don't agree with each other, but they're also, more importantly, unbounded. So that one doesn't exist. This one here, it's true that approaching from the left-hand side, it goes to positive infinity. From the right-hand side, it goes to positive infinity. So they're both going to positive infinity. So sure, I can say my limit is going to equal to infinity, right? But that limit being equal to infinity means that my limit is unbounded. Infinity is a concept of saying this is like, it's such a large number, we can't even conceptualize, we can't put a number on it. It's unbounded, it doesn't have any limit, right? If the limit itself doesn't have a limit, then the limit doesn't exist because I can't peg it down to a specific number. So the fact that they agree on left and right, because they're both going to positive infinity, is secondary to the fact that they're unbounded, okay? Okay. Right. Okay, so let's talk about, we want to be able to do some like properties, some sort of mathematical properties that we can do with limits. We'll call these basic limit laws. And they'll help you be able to process, like when you're given a bunch of functions, you want to be able to combine functions, you want to be able to do things to be able to process and analyze limits. These laws are going to help you. So we're going to make some certain assumptions. So we're going to say, that the limit as x goes to c of some function f of x exists. And I'm also going to make the assumption that the limit as x goes to c of g of x. So I'm going to assume that these limits exist, right? And then I'm going to do stuff where I'm going to combine them. Okay, so the first thing is I've got a sum. So this is like sum and difference. We're going to add or subtract. So my sum law says that if I've got the limit as x approaches some value c of f of x plus or minus g of x. Okay, so this limit here, as I sum them, exists. Okay, and what I can do is I can distribute this limit to both of these here. So I can say the limit as x goes to c of f of x plus or minus the limit as x goes to c of g of x, right? So whatever f of x is, I get a number. Whatever g of x is, I get a number. And then I can add or subtract those 2 individual limits together. If the limits have the same basic property, right, they're going to the same value, I can think about it as factoring out the limit, adding, combining like terms, and then processing the limit as a whole. So these things work in both directions here. Okay, second law, a constant multiple law. This is like a scalar multiplier law. So this is for any number. Okay, so k is just some number, some scalar. You can say the limit as x goes to c of k times f of x. Okay, that's going to equal to, I'm going to like basically bring that k out front, and then I'm going to take the limit of my function. So whatever I get from the limit of my function, and then I'm going to multiply it by k, and that's going to be my total answer. Okay, our product law says, right, I've got the limit as x goes to c of f of x times g of x. I've got 2 functions being multiplied together. Okay, this thing exists. Okay, and it's equal to, watch what I can do. I can say the limit as x goes to c of f of x times the limit as x goes to c of g of x. So break it apart. Evaluate this limit, evaluate that limit, get the answers, multiply them together at the end. Okay. I can also do the in reverse, right? So I see that the limits, if they go to the same thing, then I can pull it out and then multiply the functions together, just take one limit. If they go to different things, then you can't do that. You have to evaluate them individually. A quotient. My quotient law says, first off, I need to say this is all true if the limit as x goes to c of g of x is not equal to 0. We'll see why in just a minute. So we'll say the limit as x goes to c of my f of x divided by g of x. Now I can break this up into numerator and denominator. So limit x goes to c of f of x divided by the limit x goes to c of g of x. Okay. And likewise in reverse, right? If I see this, they're going to the same limit value. I can pull it out and then just divide these through and then take one limit. It may be easier to do it this way, or it may be easier to do it this way. You'll have to evaluate it based on the function. Okay, last law. You guys all have these here. I'm going to flip the page. Okay. So our last law, our root law. Root is another, I can represent a square root, cube root, nth root. I can represent that as an exponent. So that's what we mean by that. So if we're going to say p and q, these are just our integers. Then I can say, I want to specify q does not equal to 0. That'll be in our denominator. So then I'm going to say the limit as x goes to c, my function f of x, and my function is going to be raised to the p over q power. Okay. So what I can do with that is I can say this is equal to, watch, I'm going to bring the limit as x goes to c of my function, and then raise that whole limit value to the p over q power. That might be easier, right? Maybe it's too hard for us to evaluate this function as is, right? Or maybe if this is too hard, I can pull it out, evaluate this function, and then take the limit at the end. You'll be able to see as you go. If p divided by q gives you an integer value, then I can do, let's say this. Let's say p divided by q gives me an integer value. So I can say limit as x goes to c of x to the n, which is equal to limit as x goes to c of x to the n. So it just gives me that. Now it's the same thing, likewise. Goes to c. This is going to be x to the nth root. This is the root there, which I'll write as an exponent just so you can see what that looks like. Limit as x goes to c of f of x to the 1 over n. It's the same thing, right? Now I can pull in my limit that's equal to limit x goes to c of my function, that whole thing being raised like that. And that's if, you know, p divided by q gives me a positive, like q divides evenly into p, okay? Or if I can simplify p and q so that I have 1 over some number, that's what we're getting. This is usually just like special cases of this law right here. Okay, hey guys. Right, so let's try some examples here. Example 7, 8, 9, a bunch of these are going to allow us to take a look at these properties here and apply them. Okay. You guys all good with this page here before I go off? Okay. All right, so let's evaluate the limit here. So this, I don't have any discontinuity at x equals 2, so I can just do a simple substitution. That's going to equal to 2 to the 3 power, which is equal to 8. So always I'm looking for like a discontinuity that's going to, cause a problem that I need to do something special about. This one here, I'm going to do the sum law just to show you how it could be applied. In reality, right, you can just substitute x equals 2 into here and then apply it and work it through. But let's apply our sum law so that you can see what that looks like. So the limit as x goes to 2, limit as x goes to 2, 5x. We do these shortcuts where I can just substitute it in directly, but really it comes from the fact that I can do this. This is actually 5. This is our multiplier. X goes to 2 of x, right? So this we just evaluated in the first part. So 2 to the 3, that's 8. 5 times 2, that's 10. Plus, this is just a constant number that's equal to 7. So 8 plus 10 plus 7 equals 25. Okay. When I plug it all in, it's the same thing as breaking it apart. Okay. This here is the same thing as, I'll write it out like this. Limit as x goes to 2, this is going to look like x cubed plus 5x plus 7 raised to the 1/2 power. Okay, so it's similar to one of our power rules. Okay, so let's go ahead and do that. That's like saying I'm going to go to the limit as x goes to 2. I'm going to bring it all inside x cubed plus 5x plus 7. And this whole thing is being raised to the 1/2 power, or I'm taking the square root of it. Okay, which we just evaluated that right here. So I'm just going to plug that in. That's equal to 25 raised to the 1/2 power. Oops, sorry, which is like saying radical 25, which is just equal to 5. Are you guys good so far? Can I turn the page, or do you need a minute to keep writing? Okay, so let's do this one. We're going to evaluate this example 10. I'm going to evaluate this limit here. So this is our this is our quotient. Okay, so I'm going to break this apart so it looks like the limit as t approaches -1. Be careful. This isn't approaching 1 from the left. This is approaching the value -1 of t plus 6 all over the limit as t approaches -1, 2t to the 4th. Okay. Now I can just, let's do the sum and product rule of this one here. Just this is limit -1 of t plus the limit as t approaches -1 of 6. Okay, so I'm really going into all the details on this, okay, to help you so that you can understand where the intuition comes from when you're evaluating the limits. As you do the limit more and more, you'll get more familiar with, I can just plug it in and come up with a value. But this is why we can plug it in and come up with a value, because of these underlying rules here. This is equal to -1 plus 6 all over 2 times -1 to the 4th, which is equal to 5 over 2. Okay, this is a product and power rule for example 11. So we're going to work on that one. So this is going to look like the limit as t approaches 3 of t to the -4th times the limit as t approaches 3 of t plus 5 to the 1/3. I'm going to evaluate each one individually, right? And then we'll work it from there. So this I can just substitute. So this is 3 to the -1/4. Okay, times, right? I can do, this is to the 1/3, so I can bring that in. So this is the limit as t approaches 3 of t plus 5. And that's, I'll write it as a root interchangeably so that you get accustomed to, oops, sorry, to thinking about it that way. Okay, so 3 to the -1/4 times the cube root of, I'm going to take this limit here. I can just plug this one in. So 3 plus 5 is 8. Cube root of 8 is equal to 2. So this is equal to 3 to the minus 1/4 times 2, which I can bring it into a fraction. The negative exponent means it goes down in the denominator. Both of these are correct. I'll accept both of these here as answers, but just so that you know what you're looking at. Okay. Questions so far, guys, before we move on to the next topic? Everybody good? Great. So let's talk about a really important topic, which is we're going to start using our concept of limits to help us define continuity on a function. Now, when I think about continuity, so when I think about continuity on a function, I want to be able to think about, let's see, I've got some function, you know, it's doing stuff like this. Here's my function. We'll call it f of x, and I've got some c value, x equals c, right? And then my function actually has a value there. Like if I always think about continuity, like I put my pen or pencil down on a piece of paper and I can draw it continuously without lifting up my pen, whether it's for an asymptote or for some kind of a discontinuity. If I can draw it all in one fell swoop without having to move my pen at all, okay, there is some specific value. It's continuous. Okay, we'll say it's continuous at x equals c. Now let's draw what it looks like if it's discontinuous, right? So I've got some function, it's doing something, I'm drawing along, oop, and then I stop, and then I have to pick up my pen. Look, I have to pick up my pen and then doing something else. So this is my g of x function. This is my x equals c value, right? So look at what I did. I was drawing along, and I had to pick up my pen from the paper and move it, right? So it makes it non-continuous. I have a discontinuity at x equals c. Well, many different types of discontinuities. Okay, we're going to talk about some of them. Some of them, we can think about them simply as asymptotes, right? If I have a vertical asymptote, then I've hit a wall. Okay, I can have a jump discontinuity where my function actually takes on a different value at this point here. Okay, or maybe it's just a, you know, just a removable discontinuity where it's a hole in my function, right? I'm drawing along, I have to lift up my pen and then I can put it along there, keep drawing it. So you have different kinds of discontinuities, but we're going to use our limits to help us define whether a function is continuous or not. So limits are really powerful because as we get into calculus, we want to be able to talk about, you know, is the function continuous or not? If the function's continuous, right, I'm going to prove it's continuous using limits. I can do a bunch of stuff, take the integral, take the derivative. If it's discontinuous, I have to watch out for that spot where it's discontinuous, right? I have to do other stuff there. All right, so let's write a formal definition of things. Okay, so our definition. So we're going to talk about continuity. Continuity at a point. Okay, so I'm going to assume that my function f of x is defined on an open interval. This is a lot of words, so, you know, bear with me here. I'm going to talk it through. Interval. And that interval is going to contain our value c, right? So just like we did in those graphs, I've got my function, I've got some open interval. And the interval could be minus infinity to positive infinity, or it could be -3 to +3, whatever. It's some open interval, and it's going to contain this value x equals c that I want to look at, okay? Then, if our function f is continuous at x equals c, if our function is continuous at x equals c, it will be continuous if the limit as x approaches c of f of x is equal to, f of c, right? So can I plug in that value x equals c into my function and get a number out, right? So my limit, my left and right limits, my limit has to exist first off, and then I want my function to be equal to that value if I were to be able to evaluate that, okay? So we could also say if the limit does not exist. Okay, so this is, we're saying this function's continuous. If our limit exists, okay, and if the function value at that x equals c is equal to the function evaluated at, that means our function is continuous. Conversely, if the limit does not exist, okay, or if the limit does exist, but the limit does not equal f of c, right? So this would be the limit as x approaches c of f of x does not equal to f of c. It's equal to some number. So the limit exists. It's a valid limit. It just doesn't equal to whatever that function is going to be evaluated at. Then we say our function has a discontinuity at x equals c. So let me summarize. What does it mean to be continuous? Okay, so in summary, so to be continuous at x equals c, say for example, okay, 1 f of c is defined. Okay, I have some value. I can actually plug in x equals c. I can get some number, some actual valid value out of that. 2, my limit approaches c of f of x exists. Now remember what this implies. Look, that implies that both my left and my right hand limits are equal to each other, right? So I'm looking at my function f of x. They're both approaching the same value, okay? F of c is defined. My limit on both the left and the right, my limit exists, and number 1 and number 2 are equal. Okay, that means that the limit as x approaches c of f of x is equal to f of c. Then we say our function f of x is continuous at x equals c. So this is summarizing all the math that we just wrote up above. But before we talked about what does it mean to be not continuous. Okay, let me know. I'll give you guys a minute to finish writing that, and then we'll talk about different types of discontinuities. You guys good? I'm going to flip the page. If you need this page back, yell at me to put it back, and I will put it back. All right. So let's say the limit as x goes to c of our function f of x exists. Okay, so the limit on the left and the right are equal to each other, but is not equal to f of c, right? So our function approaches some value, it approaches the same thing, our limit is equal, right? But our function, right, at this x equals c is equal to some other value, okay? Then we say f of x has a removable, write this up better, removable discontinuity at x equals c. So this is a removable discontinuity. And what does that look like? I'll graph it. Right, so I've got this function f of x. This thing is continuous, right? Let's say this is x equals 2, for example. This is continuous. So f of x is defined at x equals 2. It's also continuous at x equals 2. Okay. Contrary-wise, if I have a removable discontinuity, my function is going to look like this. At x equals 2, looks like that. And then I'm going to define my function value. It has a completely different value at x equals 2. X equals 2, right? So my function cruises along. Oop, I've got a jump. There's a hole there. and I have a function that I define. Excuse me, I have a function. I define the function value at x equals 2. It's something different than whatever this function is. It's got a discontinuity. Okay, so this is what we call a removable discontinuity. Okay, so that's one. This is a removable discontinuity. Another type of discontinuity is called a jump. A jump discontinuity. Okay, so this means that if both one-sided limits exist. So my left-hand limit, my right-hand limit, they both exist. They're equal to valid values, okay? But the left-hand limit and the right-hand limit are not equal to each other. Start writing it in math. So the left-hand limit and the right-hand limit don't agree. They're equal to two different values, okay? Then basically, we're dealing with what we call a jump discontinuity, and it looks like this. My function cruises along. Let's say this is x is equal to 2, for example. Okay, you can imagine, right? As I'm approaching x equals 2 from the left-hand side, it's equal to a valid value. As I'm approaching x equals 2 from the right-hand side, it's equal to a valid value. But they're different from each other. Also, my function is actually defined at x equals 2. Okay, so let's do another one. It looks like. Okay, so watch what happens on this one. My function approaches x equals 2. It's equal to a valid value. The limit as x approaches 2 from the left is equal to some number. The limit as x approaches 2 from the right is equal to some number. And my function is defined at x equals 2. Defined as something completely different than what either one would be evaluated at. Okay, these are jump discontinuities, right? I had to pick up my pen and move it, and my value, my function changed. My limit on the left and the right are different. So we're using one-sided limits. To describe this function. Okay, my limit on the left, my limit on the right, you know, that's going to help me define the nature of the function itself. Okay. Removable discontinuity and jump discontinuity. Yes, give me a minute to finish writing that. You guys good with that? I'm also posting lecture videos every day too. I post them to my YouTube page, and I post them to our lecture video portion on that week on our Canvas page. So if you feel like I'm talking really fast, I believe there's an audio transcript, and there may even be subtitling on our closed captions on our YouTube page. And there's an audio transcript on our link when you follow the link to load up the video. So you can pause it and play it back, okay, if you want to be able to actually read it. Sometimes the audio transcript is funny because the words that it uses for the math descriptions can be really quite amusing. Okay, so let's use our limits and our discontinuities to talk about how we define one-sided continuities on a function. Continuity, like I said, on a function is really important, which is why we're belaboring this point here. I want to define what's called a one-sided continuity. Okay, so we say f of x is called, right? Oh, I'm going to call it both left and right. It's called left continuous at x equals c if this is true. The limit as x approaches c from the left-hand side of my function is equal to f of x. Oh, sorry, is equal to f of c. Okay, we saw that in our right? So here, this would be left continuous, right? It's defined f of c, and our limit as we approach this from the left-hand side is equal to that. This is our left continuous function. Likewise, I can do this from the right. It would be right continuous at x equals c if the limit as x approaches c from the right-hand side of my function is equal to f of c. These come into play a lot when we go to analyze piecewise functions. Piecewise functions are a really important part of engineering. We use piecewise functions a lot in engineering to describe things because the behavior will change at a given point because of, you know, some parameters that we set in terms of our definition of like a circuit or a definition of something that we're trying to describe. So let's take a look at example 12. Example 12 is a piecewise defined function. So my function is equal to, I define it like this. I like to graph these out because it helps me visualize. So I've got my x-axis and my y-axis. Should give myself more room for 5. Okay, so now I'm going to draw out this graph. It's going to help me. So it's straight linear, y equals x for when x is greater than 1. So this thing is going to look like, I'm sorry, for when x, I can read, for when x is less than 1. Okay, so it's not less than or equal to, it's just plain less than. So I have to do an open circle, and this is just a straight linear function like that. Okay. The function is equal to 3, just y equals 3 between 1 and 3 inclusive. So here's my 3 value. I put a full circle. Here's my x equals 3. 1, 2, 3. I just have a straight line like that. See that my inequalities contain equals, right? So that's how I can do the full circles there. It's a straight linear for when x is greater than 3. So I have, I don't have to worry about putting in an open circle here because it's actually defined for that point right there. So I'm going to go like this. Like that. So my piecewise function looks like this. This is just how we've defined it. So the important thing is we want to look at our transition points. So where are our transition points? Our transition points are here, look. So I've got a transition point here, and a transition point here, right? Where my function is changing, right, from one piecewise function to another. So this is going to be x is equal to 1, and x is equal to 3. Those are our transition points. All right, let's do the first one. So at x is equal to 1, okay, I'm going to do one-sided limits here, okay? The one-sided limits, I can tell that they're going to exist, but they're not going to be equal, because look at what's happening. As I approach 1 from the left, as I approach 1 from the right-hand side, it's going to be equal, different. Exist, but are not equal. Okay, so let's try it. So I'm going to go the limit as x approaches 1 from the left-hand side, right? This isn't -1. I'm approaching 1 from the left-hand side of my function. It's going to equal to the limit as x approaches 1 from the left-hand side. Now, that means x is less than 1, right? Which means I'm dealing with this function right here, which is equal to x. So I'm going to plug in, right? I'm looking my values as I'm approaching 1 from the left-hand side. It means I'm looking at values of x that are less than 1, which means I'm doing this function right here, f of x equals x, which is going to equal to 1. Okay. I can see that. So now I'm going to go the limit as x approaches 1 from the right-hand side of my function. I have to look, these are values of x that are greater than 1, okay, which is equal to the limit as x approaches 1 from the right-hand side of 3, right? So I'm approaching from here. I'm approaching 1 from the right-hand side, but that means I'm using this, oops, sorry, you can't see. I'm using this function to help me define it, which is just going to be equal to 3. So I can see my left-hand limit and my right-hand limit are different from each other, okay? I have a jump discontinuity at x equals 1. But since right and limit is equal to the function value, we can say our function f of x is right continuous at x equals 1. Remember, we're only evaluating right now just at x equals 1. So it's right continuous at x equals 1 because, right, my function value is equal to the limit value at this point right here. Okay. That's for x equals 1. I'm going to do the same thing at the other transition point. X equals 3. This is another one-sided limit. So I'm going to go like this. The limit as x approaches 3 from the left-hand side of my function big f of x is equal to the limit as x approaches 3 from the left-hand side. Okay, so I'm approaching it from the left-hand side. My function at x equals 3, so I'm approaching it from the left-hand side. Sorry, you can't see anything. From the left-hand side, that means I'm approaching, I'm on this function here, the limit of 3, and that's equal to 3. Do the same thing. My limit as x approaches 3 from the right-hand side of my function is equal to, let's take a look. As I'm approaching from the right-hand side, I'm dealing with this function here. So I'm approaching is equal to the limit as x approaches 3 from the right-hand side. I'm using this function value. As I'm approaching, I'm going to plug that in. That's equal to 3. Well, they're the same. My left and my right-hand limits are the same. Okay, so let's talk about what that means. So we've got a couple conclusions I can make. So my left limit is equal to my right limit. That's a good first step, right? And they exist. And they exist. They are both equal to f of x equals 3, right? So my big function evaluated at x equals 3, they're both equal to that. So I can conclude that my big function f of x is continuous at x equals 3. It's continuous at x equals 3. It's only right continuous at x equals 1. Okay. You guys think? I have a lot to take in. We're working on it. Okay. I think we're at our time limit for our class, so I'm going to stop here. If you guys have other questions on homework problems or things that we covered in class today, please come to office hours. I'll be happy to talk in more detail about that. Okay. Have a great rest of the day, guys.
I have a few questions about the quiz tomorrow.
Yeah, really quick.
Yeah. I was wondering, so are we not going to have class? And is there going to be like a window of time that we complete the quiz?
Yeah, that's a great question. We will have class tomorrow. And then the quiz will become available at noon on Thursday, and it will be available until noon on Friday. So it's a 24-hour availability window. It's meant to accommodate people who are in different time zones. Okay, so you'll have 24 hours within which to start the quiz, but it is timed. So you'll have 30 minutes to do the quiz, and then an additional 15 minutes to like take picture, convert it to PDF, and upload it. So the total length of time will be 45 minutes. Because we're giving you 15 minutes to do all the administrative stuff, right? And because we're all new to Canvas, if you have any problems uploading it, then do your best on uploading it, and then you can email me a PDF of it, and we'll work it through. We'll try to figure it out. But yeah, we'll have a 24-hour window.
Alright, so we're uploading it through Canvas.
Yes, you're going to upload it onto Canvas, and that's where I'll grade it. And this is my first semester using Canvas, so be patient with me as I'm learning how Canvas is working. In our previous form, I was actually able to grade it actually online so that you could see like my corrections and my comments and stuff. we'll see how that works here. At the very least, I'll be able to post your grades onto the Canvas grade page so you can see what you got, and then we'll figure out how you can actually get the feedback in a minute later. But yes.
Thank you.
Okay. But we will have class tomorrow. Yes.
Okay.
Okay.
Thank you.
All right, you guys. Take it easy. Have a great day.
Thank you.
Bye.
Thank you.